Okay, I am going to be creating the screencast to walk you through the P's analysis. We got a good amount done the other day in class on Friday, but we didn't really finish, so I want to just take you through the whole script. So what you need to do is you need to go to wherever you have the script. Mine is in my Data Science 218 folder. In the R scripts area, the P's analysis, which is going to use the P's data. I've updated the R script and I've also updated the data file so that it's a little less cluttered. So go ahead and download those two things if you already have, and replace the current versions with the old versions. So up here at the top is a bunch of explanation, but at line 26, make sure that you're in the correct directory. And then what you want to do is read in the data file. And you'll see now that the data file is simpler. And actually, we don't even really need treatment A any longer because I discovered that you can run this little line that is line 49 and 50. That will basically tell it to not reorder the treatment levels. And so you can see that the treatment levels are control 2% glucose, 2% fructose, 1% glucose, 1% fructose, and 2% sucrose. And it should keep that ordering throughout the entire script. For the most part, there's one part where it doesn't keep that order. Load up your libraries. And then once you have those all loaded up, you want to check your data on line 78 to make sure that treatment is in there as a factor and class $growth is an integer. And now we want to check assumptions. So we're going to use line 104 here to basically check our residuals for normality, and we're going to calculate residuals across all 5 treatments. So we're basically going to run the ANOVA model, which is this part right here, AOV, with growth being determined by treatment within the data file DAT. And we're going to get it to save the residuals from that in a data frame that we call res. You can see res right here. You can see all 50 residuals. They're a mixture of positive and negative residuals, and then we can test those residuals to see if they are normally distributed. We see that the Shapiro-Wilk test is not significant, so these data do not differ from normality. And we can look at a histogram, which looks more or less normal, and we can also look at a QQ plot to see if they are normal. You can do this with each treatment, but you're just going to reduce the power to detect differences from normality, so I'm not going to do that. I'm going to skip down to run Levene's test to see if the variances are similar among the treatments or not. And what we find is we have a significant Levene's test, meaning that the variances are different. So we need to do something about this. So this is an example that I took out of Sokol and Rolf, and their suggested transformation is on line 131 of the script. And so they're dividing 1 by the growth of the specimen and then multiplying that times 100. And so we're basically going to apply their data transformation. And when we get that, we see that it has added a transformed data column to our data file. Now we can recheck the homogeneity variances, and now we find that they are not significantly different. And so what we can do now is recheck normality. And what we get is, once again, a non-significant Shapiro-Wilk's test. We can scroll up and see what the Shapiro-Wilk test was before. It's 0.2164, and now it's 0.19, so our p-value has actually gone down just a tad. Once again, we can make a histogram of these data. Once again, nothing looks particularly off, and a QQ plot doesn't look too bad. So sometimes I just like to see the data, and you can see that it's keeping the order: control 2% glucose, 2% fructose, 1% glucose and fructose, 2% sucrose. So that changed to the code that I made up above. which means that I get to get rid of all of this stuff. And so it looks to me like what we did in the transformation, though, was we changed the order of things. The control, which was growing the fastest, is now the lowest mean. Sucrose, which was the second fastest, is actually now the second lowest mean. So that inversion changed the order of things. So now down here at line 168, we can actually run the analysis on the transformed data. And when we do that, we find that we have a significant overall analysis of variance. And what that means is that at least two of these means are different from one another. So in this case, the researchers had specific plan comparisons that they wanted to do. And so we can see that this is the order of the data, and we can look at what order the levels are in. So there are control, glucose, fructose, glucose and fructose, and sucrose. And so the first contrast that they wanted to know about was, is the control different from the rest of the sugars? So we'll set up contrast where the control is 4 and all of the other sugars are -1, all grouped together. The second contrast compares pure sugars to the mixture, so we get rid of the control, and we have glucose, fructose, and sucrose all as positive ones, and the mixture, which is 1% glucose, 1% fructose, as a -3. Then we want to compare among the pure sugars, comparing glucose, fructose, and sucrose. And this is a problem. And then we have a non-orthogonal contrast, which is comparing glucose and fructose to the glucose-fructose combination. We talked about what orthogonality was on Friday, and so you just want to check these things for orthogonality, and I'll demonstrate to you why the computer kind of misbehaves when you do things that are not orthogonal. So what we're going to do is we're going to create lists of each of these things, so that if we run all those and then we, for example, type in C1, we just get a list of those coefficients. But now we want to combine those coefficients into a matrix. The matrix looks like a matrix of those coefficients. Now we want to link those contrasts to the levels of the treatment. And when we do that, we get control has a 4 for the first contrast and 0s for all the rest. Glucose has a -1 for the first contrast and positive 1s for all the rest. So now we can rerun the analysis just to make sure that it's still giving us the same result that we had before. And then in this one down here, what we're going to do is we're going to run the analysis again, but in our summary ANOVA table, we're going to get it to run the first 3 contrasts. And I want to concentrate on the first 3 contrasts because those are all orthogonal to one another. And when you, whoops, I just hit a wrong button. When you run this thing, it basically gives you the overall treatment effect, and then it gives you the sums of squares for each of these planned comparisons. Now, I want you to pay attention to the among pure here. Among pure, we wanted to compare to see if there were differences among 2% glucose, 2% fructose, and 2% glucose, but you can see that it is only giving us 1 degree of freedom, and there should be 2 degrees of freedom here. And so this is a mistake in R, and I did some research on it, and the reason is that R basically compares groups that are positive versus negative. It doesn't do any splitting up of things according to what the coefficient is in front of it, even though it's calculating the sums of squares as if it is. So this is the correct sums of squares calculation, but the mean square, and as a result, the F statistic is going to be different because you should be dividing the sums of squares by 2 here instead of 1. So that would then result in F value that was significantly different than this one. It's still going to end up being a significant comparison, but the p-value is also going to be different. So you need to calculate those by hand. If we add the 4th contrast up here, the glucose plus fructose versus the glucose-fructose mixture, we see something interesting in the output. we see that it doesn't calculate anything, and it's because there are no sums of squares left. If you add up these three sums of squares, you see that they will all sum to 6.408, and there are no sums of squares available to run this analysis. It's running it and giving you this value, but essentially it's just a rounding error in the computer that's doing this. And so that's one of the reasons that it's not orthogonal, is there are just simply no sums of squares left to work on. You can capture this analysis, and when you run this code here, capture output, it will take the first ANOVA that we ran with the multiple comparisons, and it will output it to a file called P's output CSV. So if we go here, there should be a P's output CSV file. And in this file, it has all of your numbers so that you can basically work with this inside of Excel. And what you'll probably want to do is you'll probably want to, it's not very clean because this is all in one column, unfortunately, but it puts it out into a place where you are not having to cut and paste everything. And so once you are over here in Excel, it has all the numbers, and of course you're going to want to correct this degree of freedom right here. That should be 2 degrees of freedom rather than 1 degree of freedom. Whether that's something you want to use or not, or you want to just copy it down and fill out an ANOVA table. If you hadn't done these analyses looking at these planned comparisons, one of the things you might have had is just wanting to know which groups are different from this. You can use the Tukey-Kramer test, which is what we introduced in class on Friday. And once again, this gives you all of the possible combinations of means being compared while controlling family-wise confidence intervals. So glucose is different from control is different from fructose, control is different from the 1-to-1 ratio, and control is different from sucrose. So basically control is different from everything, and sucrose is different from all of the simple sugars as well, and is also different from the control. You can also do these pairwise comparisons in a different package called Agricole, I guess is how you would pronounce it. The nice thing about doing it this way is that it gives you the Tukey's test, and it actually groups things by groups. So sucrose is by itself, the control is by itself, and then the 3 simple sugars are all grouped together in group A. And so that's going to be useful later when we go to create a graphic where we can illustrate to somebody what's different from what. So let's just remind ourselves again that we have 10 observations in each treatment. They're ordered in this order. These are the means, and these are the confidence intervals over here on the far right. We can add the groupings to that list so that we have a grouping variable. We won't use it for this next plot, but we'll use it later on. We can graph the results, and once again, this looks counterintuitive because we know that under control conditions, the plants grew the most, but that's because of this transformation that we did for the data. So it would be better to not have counterintuitive graphs and rather meaningful graphs. So what we can do is after we've transformed data, we can take the summary data and then back transform that data into the original units. And so this is our transform data. We can back transform the mean just by multiplying, dividing the transformed data into 100. And what that gives us now is a set of means that are much closer to the original means that we had. And then we need to calculate the upper limits and lower limits. And so we basically are going to take the mean of the transform data, add the confidence interval to it, and then transform that thing to give us the lower limit and the upper limit. It will be subtracting that because everything is inverted. Then what that gives us is that gives us upper and lower limits, but then we need to know what the differences are because that's what we actually want to plot. And so now we have upper level range and lower level range, and you see that the numbers are slightly different because of the result of this transformation. The upper range goes up just a tad further than the lower range goes down. And that's true for all of these things. And that's the result of the transformation. We'll once again go and add the grouping letters from the 2-keys test. And now we're going to re-plot all of this. And I've added a line in here to add the grouping data from ciplot.group. And so when we do this, what you should get is you should get a nice figure that has your means plotted. They're in the original units of growth, shows that control is highest, sucrose is next highest, and all the rest of them are not significantly different from one another. And it has put the labels showing you which groups are different from one another and not different from one another. And if you were writing a report, you would export this, for example, to a PDF plot. We might call it P's. And when you then go to your folder where your data are being run from, you will see a nice PDF in your folder that is the P's data set. Analyzed, you might actually want to clean up the labels. Oh, I must have changed that at some point. Well, let's go and fix this right now. Go to scale X discrete, and what we want to do with scale X discrete is we want to add labels. Let's go and remind ourselves what the syntax is. So what we're going to want to do is just add the names in here, which is control 2% glucose, 2% sucrose, 1 to 1. I'll do it in quotes. And what that should do, I think, if I've done my work correctly, is run that. It should no, that is not what it did. Let's see, I need to figure out what I did with that. Let's see. Sorry, I'm messing this up now. Sometimes I forget how to do things, and that is irritating to me. Ah, it's labels, not limits. That's my mistake. Labels, and it also helps if you can type correctly. Nope, that didn't do it either. Once again, it helps if one can spell. Yeah, there we go. So now it has a nicer look to it, so that when we go and look at it in our output, we see that we have nice, well done labels on our x-axis, and you might want to change the size of those. You can do a variety of things to them, but now you can paste that into a report that you might be making, or a publication, or whatever. Once again, it shows you everything that you need to know. It's in the right units, and it's relatively clear and easy to read. So, and with that, I think that's about it for working through the P's analysis. I'm going to have a write-up posted that is basically how I would want you to write up the temperature data, and it's going to be very similar to the way I want the write-up for the P's data is going to be very similar to the way I want you to write up the temperature data, the Gecko temperature data. So email me if you have any questions with that, and I'll do my best to answer them.